Hello everyone, welcome again to our course AI for Healthcare Experts, where we describe AI concepts for healthcare specialists, nurses, doctors, clinical researchers to be able to build their own models or to work confidently with AI that introduce now more and more to the hospitals. We do not focus on large language models like ChatGPT. We describe overall different AI concepts, machine learning models, and talk about different concepts that are relevant to any types of AI and not only. And this video will be, I think, one of the most important in the whole course. So it would be one of the most difficult, I think, but I will do my best to make it as easy as possible to reduce mathematics and as much as possible to make it simple. So today we will talk about metrics and why it is important, because like one of the main questions that are always asked by clinicians if you try to introduce your AI to workflow, especially by ethical committee, etc. So the main question they ask is, what will happen if your AI will make a mistake? And the question is wrong, because not if, but when, because any AI will make a mistake by default. And not only AI actually, because people do mistakes, and any diagnostics in healthcare and not only make mistakes. So today we will not talk about AI. We will talk about cancer screening test that gives scanned person risk score from 0 to 1, and assume that score above threshold 50 will be classified as yes or no, like cancer or no. And obviously we will have some true positive amount. So assume we have like 1000 people, prevalence of cancer like 10.9%, so pretty high. Like this is theoretical scenario. We will review real world data later in this video. And we have true positive. So score was more than 50 based on test, and cancer indeed, patient indeed had cancer. False positive, score was more than 50, but there was no cancer in this patient, and this is called false positive. False negative, when score was less than 50, but patient had cancer. And true negative, score below 50, and there was no cancer. So these main things, main outcomes based on which all the metrics are calculated. And things that are very, very important, accuracy, and to understand what these metrics mean. So how many people were classified overall correctly? So this is accuracy. It's true positive plus true negative divided by all, and this is we will get some number, like some percentage. This is one of the most unreliable metric for machine learning, because usually we have, especially in healthcare, usually we have quite a lot true negative, and like this amount, and usually they detect it well. So if we have prevalence like 0.5%, we will have only like 50 patients, and like with some disease, and 950 without. And we can say that 975 were without disease, and we like identified only half of the really cases, and we still will have like really high accuracy, almost 100%, but still will lost like half of all cases. So be careful with accuracy. We need more parameters, and one of them is sensitivity. How many patients with cancer were detected? So true positive divided by true positive plus false negative. So which percentage of patients with cancer we really identified? And 78% is actually quite well result. Specificity. How many patients without cancer were correctly classified as negative? So we didn't raise false alarm. So patient didn't have cancer, and we said, indeed, patient doesn't have cancer. So true negative divided on true negative plus false positive, because false positive, we said that they have cancer, but in reality they don't have. So this is some specificity. Precision, also called PPV, positive prediction value, among positive tests, how many patients truly have cancer. And this can be very tricky number. So we have true positive divided by true positive plus false positive. And we see that it's only 40%. And sometimes these numbers can be like 10% or even worse if it's many false positives. So we will see how it happens. True negative, like among negative tests, how many patients truly do not have cancer. So this is usually pretty high number. So these metrics, we need to know to correctly use our model, and we will understand why. So that's how it looks actually. So we have, for example, some population, like each dot around 2 persons. And we have like this how detected, this is false positive, and this how based on threshold, for example, we separated like cancer present, cancer absent, and this will be then false negative. This green above the threshold will be false positive. We can change threshold, and then metrics will adapt a little bit. So we can try to do it. So we can change the threshold a little bit. So for example, we adjust threshold. So let's rerun it. So we can increase, for example, threshold to 60, and we see that our accuracy significantly increased, but sensitivity dropped because we didn't notice a lot of cancers here. And but our positive prediction value is pretty high, so our precision quite high, because we almost did not lose any. So we almost don't have false positive, but we missed a lot of real patients with cancer. So if we do move threshold on the left, so we have so or even less, like okay, every patient scored like with threshold above 30. We have super high sensitivity, so we detected almost all cancer patients, but we were like very wrong half of the time, and so each fifth patient, so only less than 20%, so only we said about 100 patients that they have cancer, and only 20 of them truly had cancer, but we almost didn't miss anybody. So this is actually, in some cases, it's pretty okay. So if additional diagnostics is not expensive, and to miss early patient with cancer is extremely risky, so this is not bad result. So that's why important to know how we want to use the model. Then we need to set threshold properly, and that's why we need to know more than accuracy. So because, for example, if for us we don't want to miss any patient with cancer, accuracy 53% will be better for us than accuracy like 92%, because in this case we missed like half of all patients with cancer. So this is bad, and that's why we need to know more about models and how to use them. Important that we didn't change model, we changed only threshold. So what, as you remember, we talked that model never says you does model has cancer or does a patient have cancer or not. Model provides some score, and our goal to make interpretation of the score. Again, if we have different prevalence, it will be significantly different distribution also, and our metrics also, our thresholds can be very differently. So this also important to take into account. Let's move further. So that's overall how usually metrics behave with different thresholds. So we see that, for example, positive prediction value grows, obviously, but actually not always. Almost always specificity grows with when we move threshold further, and sensitivity falls again because we focus only on high risk patients, so we miss a lot of them. So this how threshold change affects metrics. This is really important to take into account. This is very interesting slide, and that's what we want to also take into account. That's what I said, cancer prevalence. So we have the same model, we have the same threshold, sensitivity, specificity fixed, so nothing changes, like model fixed. But because of cancer prevalence in population, our positive prediction value can range between 6% to 69%, just because of different frequency of cancers. This is extremely, for me personally, it's very unobvious that we don't change anything, and just because of the type of population on which we implement our model, we will have a very inaccurate model to very useful, like extremely helpful model. At the same time, nothing changes actually. Only population and cancer prevalence. So this is really important to take into account when you choose and evaluate model and choose your thresholds. And this is something that something interesting to know, because this is unobvious for me, at least. Maybe for you it's okay, but for me it's really unobvious. And again, we didn't talk about AI at all, so we talk only about cancer screening. Why? Because when we talk about AI, absolutely the same, nothing changes. The only thing, we use a little bit different things with AI, so we can also make cancer screening, we can sepsis prediction, we can predict deterioration of patient in intensive care, or we can classify waveforms like ECG or flow pressure waveforms and urine ventilation. And metrics and logic, how should we evaluate models, completely the same as we work with, for example, cancer screening methods or any other diagnostics in healthcare. And we have all the methods, metrics, methodology, how to evaluate diagnostics tools, like for dozens of years, and we should implement them to AI. So that's good news, nothing new. We have all the tools for correct evaluation. And that's for a real example from real world German screening study. So almost 500,000 women, 12 screening sites. There was screening without AI, and for cancer screening, so 5.7% was cancer detection rate, like per 1,000. 38.3 per 1,000 were asked for additional tests, for additional screening. So current screening method said that 3.83% women have cancer, though only 0.57 really had cancer. So positive prediction value only like less than 15%. so that's what we talk about. So each only 1/6 of all women really had cancer. So 5 out of 6 they were called. They expressed additional tests. They obviously were nervous, but like it didn't have actually sense, but because they were healthy. And that's current method without AI. So that's what we do, and it already exists. So things and narratives when said that AI is inaccurate and it provides like alarms fatigue or excessive cost. So that's actually not true, not always true, because current methods they also not perfect. And the design of the study showed that when additionally to current methods some AI was used, detection rate increased. So it was 6.7 compared to 5.7. Recall rate decreased, and positive predicted value increased. So actually, with AI, there were less false positive, less false negative. So pure benefit for all, for patients, for healthcare system, and for doctors. So that's one of the real world implementation, how AI works together with current methods and how they complement current workflow. So, and that's how we can evaluate AI also with the same methods as we evaluate other diagnostics. So if AI makes it better, then it's good. If not, then we need to train it more or train on different data, or we should not use AI, for example, in this workflow. Maybe it's already not bad. So I hope this episode was not difficult. It was really important. I think maybe we will do something else similar later, but I hope it was helpful to understand a little bit better how to correctly evaluate AI models in your practice based on your specific task that you want to improve. Follow us on YouTube, on LinkedIn, ask questions, like, share between your colleagues, and of course provide feedback. I really appreciate, because I want to make this video episodes as best as possible, as understandable, as useful as possible for you to make our work and our process of improving healthcare more efficient.